Hi everybody. Today we are going to see a graphical method for the estimation of statistical parameters. This graphical method works very well together with practical rules. These practical rules for estimation of parameters from any statistical distribution are, for example, as you can remember, for the normal distribution, to take 50 data points or data measurements and never less than 30. This would give us a very rough estimation, and of course we won't never know exactly how to stop or when to stop taking more sample. This graphical method would tell us when we have a quite good estimation and when we can stop taking more measurements. The first example we are going to see is, of course, for normal distribution, and this is explaining, this text is explaining this practical rule that tell us to take 50 data points or never less than 30. To show us how it works, we have generated a normal distribution in the first example using the Excel tool that we have for these purposes, a normal distribution of mean equals to 1 and standard deviation of 1 as well. So each data point we have here is calculated from all the data points that have been generated with the Excel tool. For example, this point, the first point, is in the second position, so it means that it is the mean of the two first data points. And then the third one, the mean of the four first data points. This would be this one. So this is the mean calculated from the four first data points, and so on. So as you can see, this is of course a graphical method. When the value of the mean of the estimation is converging, so it is getting more stable, then we would make the decision of stop taking more sample. So in this case, we would make the decision more or less here, that the graph is telling us that the value has already converged. So it would give us a quite good estimation, as you can see, of 1.13. So the true value, as we have already mentioned before, is mean equals to 1. So quite good estimation. The practical rule would have given us a slight rough estimation of 1.39 when the value is 1. So we would have improved our estimation in this case using a graphical method. The main contribution of this method is the fact that you are not going to need any statistical package or any. You can make this estimation and this graph even manually. We have used in this case Excel to generate the distribution and to generate the graph itself, but the data points in the reality, in a real case, would have been taken from the process or the population, and then we can make the graph even manually. This is the real value of this graphical method. Then, as we have already mentioned, and this is the illustration of what I have mentioned before, that it works for any statistical parameter. Here we have the convergence of the standard deviation from the same population as we have shown before. So this works as well for standard deviations. This is the first estimation, and then, as you can see, it is showing a lack of stability until the estimation converges more or less to the real value of 1. So in the same case, this is another example for mean. This is a different distribution of mean equals to 1 and sigma 3. The standard deviation is 3. So we would need more data point because the variability of these measurements are bigger than the example shown before. But again, the graphical method would give us the estimation of 0.9. That would be a lot better than the estimation using the practical rule of taking 30 measurements. That would give us 1.65. In this case, we have improved a lot more than in the example before shown before. For a standard deviation, the same, more or less, when we have around 100 or less than 100 measurements, then we would stop taking measurements, and then it would give us an estimation of almost 3, a lot better than the estimation using the practical rule, of course. That would give us an estimation of 2.50. And with the example of standard deviation of 6, we would take more samples, and again the estimation improves a lot from the practical rule. A very easy method to estimate any statistical parameter. Standard deviation. And it also works for attribute data, not only for variable data. Poisson distribution, only to refresh what Poisson distribution is when we have, for example, defects per unit, when we are measuring defects per unit, or when we are measuring something over a certain unit. It doesn't need to be defects itself, but the most common example is defects per unit. Again, this is showing us that we would need more than 300 measurements to estimate a lambda, or a parameter of defects per unit, equals to 1 in a Poisson distribution. The practical rules tells us that we would need at least 100 measurements that would give us, in this case, quite good estimation at well, not too bad. With defects per unit of 3, then the practical rule would give us a quite good estimation as well in this example, but the real value of this method, again, I have to say that we have the certainty, or almost the certainty, that we can stop when we have a quite good estimation. And we can show to everybody how it works and why we have stopped taking more samples. Another example with defects per unit equals to 9. In this case, our estimation would give us 9.1, and the practical rules also works quite well. So the conclusion is that with Poisson distribution, the practical rule of taking more than 100 units or slightly more than 100 units works quite well. Binomial distribution. Let's refresh this concept. Is when we are using the proportion of defective units, and the attribute is okay, no okay, go, no go, or these kind of things. When we have okay, no okay, or go, not go, or the variable can take only 2 values. First example with 50% of okay and 50% of not okay parts or whatever we are measuring, and each point represents the value of the distribution, and the sample size of each point is n equals to 1. So when we have 2 values, then we have 50% of okay and 50% of not okay in this case, and then as you can see it is working quite similar to the rest of the parameters we have already seen so far. Then we would need, for a good estimation, almost 200 units. Then the practical rule that tells us that for attribute data taking more than 100 would work a lot worse than the Poisson distribution. In this case, the practical rule would have given us an estimation, as you can see here, of 0.47. That is more or less the value in these points of here. This is 100, and then this is, as you can see, it is under 0.5. So this is not, it would give us not a good estimation. Okay, but not so bad estimation. What happens when we are trying to estimate a small proportion? Let's see what happens with 10% of no okay parts. Then here the graph is telling us that to stop more or less at the point of when we are over 300 units, and then this would give us more or less the exact value of the parameter. And with the practical rule it is working quite well again, and it would give us 0.13. That is not better. It is it cannot be better than the estimation using the graphical method, only using the practical rule, because the graphical method is telling us when the parameter is converging, of course. But in this case, it would work quite well, the practical rule. But with binomial distribution, as the parameter is getting smaller, the estimation using the practical rules, it is getting worse and worse and worse. Let's see what happens with a proportion of 1% of no-OK parts. Then, to show this, what happens, we have had to generate the distribution using a subgroup size for each point of 100. Because, as you can see here, the graphical method would tell us stopping around 4,000 samples, 4,000 units. So it is obvious that in this case, using the practical rules, it will give us a very bad estimation of 0.005. So in this case, the graphical method would save us, let's say. So, conclusion. This graphical method, used along with empirical rules, practical rules, is very useful and increases the quality of estimation of parameters for any statistical distribution and any statistical parameter when we don't know anything about the true value of the parameter. It gives us the best estimation using the correct sample size. Sometimes it means using less resources than with the use only of practical rules. Sample size for the estimation of mean is sensitive to the value of sigma. As sigma becomes bigger, the sample size for mean estimation increases as well. In the Poisson distribution, we would need less sample size as DPU gets bigger. But I have to say in this case that, as we have already shown, the Poisson distribution is less sensitive than the rest. The sensitiveness, I'm talking about the sample size, of course, in this Poisson distribution. Binomial, the sample size for the estimation of the proportion p is very sensitive to the value of p. As p becomes smaller, sample size needed for its estimation becomes bigger. And as I have already mentioned before, I have generated these all distributions using the tool for parameter generation from Excel. This is all for today. Thank you for listening. Bye bye. See you next time.